This is the Discovery Files podcast from the U.S. National Science Foundation. Many of your modern-day conveniences depend on spatial data. From weather apps to maps, Geographic Information Systems, or GIS, are the computer-based tools used to store, visualize, analyze, and interpret geographic data. Information about roads, topography, weather conditions, landmarks, and businesses are organized into layers that can be combined and displayed on maps. The U.S. National Science Foundation has played a central role in the technology's development and growth, from the 1988 establishment of the National Center for Geographic Information and Analysis, or NCGIA, to the 1990s establishment of the Center for Spatially Integrated Social Science and the National Center for Ecological Analysis and Synthesis. In the last 2 years alone, NSF has awarded about 180 grants, totaling more than $83 million, to support research related to GIS, in fields ranging from geography to math, computer science, geology, anthropology, and education. We are joined today by Jack Dangermond, a pioneer in the GIS space who served on advisory boards for the U.S. National Science Foundation and the National Center for Geographic Information and Analysis. Alongside his wife Laura, he founded the Environmental Systems Research Institute, now known as ESRI, in 1969. Today, their proprietary software is among the most popular in the field. Mr. Dangermond, thank you very much for joining us today. I would like to start by asking you about the role evolving technology has played in the GIS space.
Yeah, well, I enjoy this amazing privilege of having lived through half a century of GIS. It went from mainframes to mini computers to workstations to PCs to servers, now to the web. Each of these generations of technology heavily influenced the basic concept of putting geographic science into a computer. That concept was really birthed during the 50s and 60s. People like Waldo Tobler kind of pushed the edge of geography with quantitative revolution of geography. And they certainly inspired me in my work. But the technology is a second dimension of it. I sometimes think of there being a kind of triangle. There's the research side, there's the technology side, and there's the application side. And this triangle, instead of just being an equal-sided triangle, sometimes gets distorted. Sometimes research grows and then technology catches up and applications are beneficial. Sometimes applications push forward. Sometimes the basic technology changes things. And if you put this in context of science, there was a famous saying once that every innovation in technology represents an advancing method, which of course affects fundamental science. And that's largely what's happened in GIS. We started really with the idea of abstracting geographic information and layers, putting it into the computer. And with each advance of technique, meaning mainframes to minis, applications changed and the science of understanding geography changed. So I would simply say what happened with the invention of mini computers is there was an enormous jump. There was maybe 24 mainframe computers using geography and computer map making in the world. Maybe that's too few, but that was my experience of it, largely in oil companies or a few academic centers. When minis came along, the technology was allowed to enable it to go into departments. And we saw the birthing of geographic departments, but also in cities, the planning department, and in forestry organizations, they could actually afford to buy a mini computer. And in terms of the methods that happened, many computers had interactive graphic terminals that allow you to actually interact with the data instead of doing batch processing. When workstations came along, that opened up many more people. It was probably an order of 10 in each of those cases, maybe even 20. So we went from a few dozen to a few hundred to a few thousand. And then when a kind of small version of workstations came along called PCs, it really just exploded several orders of magnitude. So it changed not just the technology, affordability, and ability to interact, changed the method. It changed accessibility, changed affordability. And so it spread. And now with servers and especially with the web, it's exploding. Tens of millions of users, and the applications of it are reaching almost half of the world's population. An example of this is the COVID map from Johns Hopkins. We stood it up inside of ArcGIS Online on a server in a cloud, and it was looked at 1.4 trillion times. People were looking at it 10, 12, even 13 billion times a day. And the impact of this on understanding of COVID was amazing. People grew from, it's just a little thing happening in China, to the idea of this is really a pandemic and how does it relate to me? So spatial literacy resulted from this amazing step of putting one of our dashboards in front of all the eyes of the world. And that same thing is happening, frankly, in other fields, like in climate change or in loss of biodiversity or in big issues of agriculture. The shifts that are happening as a result of climate are remarkable. I would say we're a little off the subject of advances in technology, but I'll simply say, going back to this triangle, each advance of technology or technique advances science, and it also advances the applications. And that's the state that we're in today. And it seems like my entire life has been technology focused, but applying it on that other side of the triangle has been really important.
What was your role in the formation of the National Center for Geographic Information and Analysis?
I started ESRI in 1969, and at that time, our tools were really, I sometimes have described them as homemade software, because there were no software companies at the time. There was really just open source coding, and we did that for about 10 years, driven by people who would actually give us funding to do a project, sometimes locating a new town or a site for a power plant or doing environmental assessment studies or even land use planning studies. As a landscape architect originally, this fascinated me because I could actually apply the tool to these applications of integrated planning. Fundamental to this was the idea of holistic planning. I like to call it the geographic approach, where you can bring factors from the environment together with social factors and also factors about the economy. You can bring all three of these things together as maps, and you can overlay them. And that overlay or intersection of data or integration of data can give very interesting information for planners who make decisions. This is fundamental to GIS, actually. So in those projects that we would do for a small geography, sometimes for a city, they sort of got bigger and bigger, sometimes even a whole state, like the state of Maryland, a whole state planning exercise, or even for a whole nation. This work that we did, inventing advances in the tools and applying them in various ways, was done without the benefit of a science base. I mean, we had geography, and we embraced that, science of our world. But we had to sort of make up aspects of what we were doing. We had to invent data models, not knowing totally what they were about. After about 10 years, people began to notice our work, and it was interesting. I'm not saying that other people were not doing research in this field either, but they began to say, I want some of that stuff. At that time, we began to work on actually a product. So ESRI at the time had about 100 people doing project work, and we said, let's take all of our resources and spend it on creating a product that allows other people to do the work that we were doing. And that was an enormous transformation in our organization. And we started to sell this product, and it became quite popular especially during the 80s and then the 90s. And just now we have millions of customers that use it. But in that delicate time period from probably 1975 to the early 80s, my colleagues in the academy, people like Dwayne Marble, Roger Tomlinson, who was not in the academy, but certainly had a strong appreciation for science, and Dave Seminet, a great remote sensing professor at Santa Barbara, began to think and self-criticize the work we were doing. And the truth is, it didn't have the strong research foundation to balance out this triangle of applications, research, and technology. We were evolving quickly on the technology front, but we didn't have the science foundation. So the triangle, if you want to imagine it that way, was becoming weaker at the research level. So I asked some good friends of mine in the Earth Science program at NASA to give us a small grant of $17,000 to hold a specialist meeting. And we did this in Palm Springs, and it was Ray Boyle, who invented digitizers, Dave Seminette, who really was responsible for remote sensing and geography innovation, Roger Tomlinson, Dwayne Marble, Dr. Ken Smith from the University of Redlands, and myself. And we spend a week together talking about this subject. And the reality is, Dwayne particularly argued that until we get NSF funded and recognized work going on in this field, it's going to be continuing to be a technology-driven field. And while there'll be clever applications like computer maps made and so on, it won't have the broad-based science foundation that's necessary. So we talked this issue through for a week. At the end, Roger Tomlinson had recorded all of this and his wife transcribed it. And Dr. Smith then took all of this week of transcriptions and boiled it down to 33 core things that needed to be done at the research level. And this became a wonderful document. It became actually one of the lead documents that was submitted to NSF. That led to the idea that a national center should be established, and ultimately to the whole NCGIA.
How has the NCGIA impacted the field?
It gave GIS the scientific footing and the recognition in the scientific community that geography mattered, and also the geographic approach to applications had merit. And up to that time, geography was just another thing that people studied, and it got some attention by NSF occasionally, but not really. I'm not saying that geography wasn't recognized, but I think the technology had this propelling effect, advancing the fundamental science, because it was suddenly recognized by the thousands of applications of GIS that the science foundation for these tools turns out to be really interesting, a very vital piece of it. So we moved from the idea of GIS as an information system to geographic information science. And this expanded thinking at NSF, it expanded thinking across the academic field. Now, a major strategic decision was made by Michael and his team going after this center. The strategic decision was basically this: not to do it alone, to create a center that was multi-university based. And it would be housed at Santa Barbara administratively, but it would involve Buffalo and would involve University of Maine. But also his thinking was amazing, actually, setting the national research agenda for geography in a quantitative setting, and particularly for GIS with this two-headed meaning, information systems and information science. This was quite successful, in my view. That center turned out hundreds and hundreds of papers, but also many books. At the same time the center was being carried out, another dimension was emerging, and that is GIS. Instead of a few hundred GIS systems in forestry or niche areas, it became quite recognized for its application value. So I would simply credit this center as being one of the foundation points for the explosion of GIS and also the geospatial revolution, which includes imagery and remote sensing of various types, GPS, all of these industries. I mean, our business today is several $billion, but we also drag with our little business about a $28 billion ecosystem of applications, including data and people that build on top of our core. That has something to do, I can't really explicitly describe it, with the fundamental research that was carried out at the center. For the triangle to continue evolving, there had to be that science spread out. So it had more stability. It had more recognition. Looking ahead, I see that it's actually just beginning. The way geography is now going into computing, some people would just say, computer maps or the Google Maps or that sort of thing. But actually, geographic science underneath these maps, the applications, the forecasting, the modeling. Sometimes I describe our own business as we help keep the Swiss railroads on time. We manage the sewers of Paris. We manage the subways of New York. Electrical power, like 90% of it in the United States or in North America, is run based on our systems. 32,000 cities use our platform for running their cities, keeping things on time, understanding the land use plan. And then in the area of national defense, geography, GIS is keeping our country safer. And in terms of education and the value of education, you know this, there's like over 12,000 universities that use GIS as a teaching mechanism at higher ed. And then there's tens and tens and tens of thousands of K-12 schools that we're increasingly putting GIS into with our partner, National Geographic Society. So I see that the NCGIA and National Science Foundation's investment has had enormous leverage, perhaps one of the most leverageable stories or perhaps one of the most leveraged investments that NSF has ever made. I mean, I'm not suggesting that it parallels some of them that have been so successful, but this one, from my perspective, has been enormously valuable. Valuable for me, of course, but valuable for the industry, but then valuable for these millions of users who actually use it. So from an American nation investment perspective, well, this was a good one.
You mentioned some of the educational uses. Can you elaborate about how the GIS workforce has been impacted by the educational aspects of NCGIA?
There were many initiatives there, but one of them was to build what's sometimes referred to as the core curriculum for teaching geography and geographic methods. I forget what they came to call it, but it produced hundreds of lesson plans for teaching data modeling, visualization, computer mapping, spatial analysis, all the kind of components. And that curriculum was open sourced, made available. NSF partially funded it. We partially funded it. And it has resulted in spreading of methods to teachers who could easily take GIS tools and teach the whole GIS profession. I mean, there are hundreds of thousands of what I would call GIS professionals today. And many of them came out of these thousands of schools who have GIS programs. And the kernel of that, again, came from the insight that Michael and people like Karen Kemp put their heart and soul into building collections of teaching methods, but also best practices explanation of what is a GIS and how is it used. And we build on their shoulders, all of them today, in both K through 12 education, but also in higher ed education. Now, ESRI has a training faculty and web classes of all types, but they also train roughly 650,000 courses every year. Many of them are on the web, but also the faculty here add up to nearly 100. They're doing that on, again, the shoulders of what has been built from the good science work that started there at Santa Barbara and Buffalo and Maine.
How have geographic information systems evolved as applications and technologies have advanced?
GIS has evolved into three kinds of systems. One of them is a system of record keeping, and it's best to think about land property boundaries or polygons. Every time somebody subdivides a piece of land, there's a transactional update on that system of record. Similarly, in forestry, there's polygons of forest stands, or in state boundaries or census areas. These are polygon data sets, and they are systems of record keeping administratively or scientifically. Then GIS is used as a system of insight, and this is spatial analysis, and people overlay data sets, some of them systems of record or some of them coming in from sensing areas, and they analyze the relationships and the patterns. They make interpretations of them. These analytics or spatial analytics turn out to be one of the powerful value benefits for doing GIS, and people like Starbucks locate all their stores with them. The third application area is systems of engagement. So it turns out that maps are a language, and the COVID map is an example of how everybody could very quickly understand what's happening. Air pollution maps, population density maps, just about anything can be mapped. From a spreadsheet now, we can make a map very easily. And so people are mapping business activities, hot spots for this, et cetera. That's very engaging to people. Citizens are seeing what's happening in a city from a policy perspective or a data perspective, and that's very useful. The bigger situation is being able to take maps from many different organizations and put them together, looking through those maps to understand the complexities of our world, whether it's ecological complexities or dependencies or supply chains or where things are not equitable in relationship to where people are spending money for infrastructure investment. It's almost endless. it's almost up to your imagination. I mean, I often say that it's up to your imagination. In climate change, the White House recently asked us to bring together federal agency data on climate change and overlay it so that local governments could understand what's going to happen over the next 25 and 75 years. So looking at forecasts and heat, forecasts and where more flooding might occur, forecasts and where sea level rise may occur, forecasts on wildfires, these sort of difficult challenges that we're going to be facing as a nation and as a world, bring them all together as maps. Well, why did the president ask us to do that? Because he developed a $1.3 trillion bipartisan bill, which was passed, that would allocate infrastructure money to all the local governments and state governments across the nation. And he wanted to make sure that if this money was being approved in this zip code, that it wasn't going into a place that's inappropriate, considering climate change and also social equity. So this is a perfect national web GIS system that has been deployed, and thousands of local governments are using it as a screening mechanism to do kind of a dynamic environmental impact statement before they apply for a grant to get infrastructure funding for their community. GIS is actually fundamentally in the understanding business. It's all about bringing all the sciences together, integrating them, and then supporting actions. So GIS has scaled from doing little projects to doing systems of record keeping and analytics for science to this idea that it's becoming now a kind of infrastructure for our nation.
You've mentioned some of the ways GIS can inform climate response, and I wanted to ask you about conservation. You've established the Jack and Laura Dangermond Preserve near Santa Barbara in California with the Nature Conservancy. And I wanted to ask you to tell us a little bit about the importance of conservation.
I grew up in a nursery, actually, and I've always been close to plants, growing them, selling them, and so on. And I thought I would be a landscape practitioner, but in university, I learned about the other meaning of landscape, meaning geography. In other words, landscape as a noun rather than as an adjective or adverb. And I began to think about the landscape. My family, including my brothers, were all great conservationists. He was a park planner, an open space planner. So it's in my DNA to care about nature. And personally, I just love it. I'd love to be in nature, get refreshed by it. And I suspect that everybody is. One of my good friends, Ed Wilson, described this as being a biophiliac. He said there are some people that are really biophiliacs, but actually most people are biophiliacs. They surround themselves with little philodendrons in their apartment in New York or whatever. It's quite charming to me. But specifically answering your question, in my life, I have always planted trees. I've always developed little park plans for my own local community, and then worked in conservation projects actively. My wife and I looked at a property just above UC Santa Barbara for almost our entire married life, and it was called the Bixby Ranch. It's about 25,000 acres of land that was owned by one family back into the 1800s. And we tried to buy it a few times, but we never had enough money. Finally, we did have enough money, and we were very fortunate to acquire it in partnership with the Nature Conservancy. So now it's a permanent preserve area. Now, that preserve is interesting because we decided to turn it into a living laboratory. And so it is being wired up as a digital twin of nature. The streams, the trees, the wildlife that's there are very much in a pristine state. One of the only places along the western part of the United States that are in such a state. So we are digitizing everything, digitizing colors of the bears and the lions, measuring with great fidelity changes in air temperature, stream flows. And this preserve is going to be an open science laboratory. So far, about 100 institutions, including NASA and Smithsonian and others, are coming here to do fundamental work. And one of our rules is that as you do your work, you need to spatialize it, of course, and it also has to be open science so that any transaction, let's call research a transaction that occurs there, is shared with the next researcher that will come. And that's quite interesting. These researchers now are getting together every year, sharing the results of their work, and some of them are in archaeology, some of them are in the dynamics of dune movement, some of them are in restoring one of the streams into an anadromous stream. It's a marvel. The purpose of this is to, again, be a place to do fundamental research, but also to come up with a pattern of using all of this information to do better conservation area or preserve management. TNC likes this idea a lot because they can develop templates of practice here, experiment with things like cattle grazing or not, and see if there's other patterns of use that they can apply in their other conservation efforts.
Special thanks to Jack Dangermond and Margaret Pizer. For the Discovery Files, I'm Nate Podker. You can watch video versions of the Discovery Files and much more on our YouTube and Roku channels by searching at NSF Science. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.